Pannaan tää näin. Ok, eiköhän sitä voisi sitten aloittaa. Alright, so this Matlab file is called least squares 2. It's a direct continuation to our file least squares 1, where we looked at systems of two equations. Here we look at linear systems of three equations and two variables. So, well, actually, so of two variables and three equations and solution using least squares. Still March. Okay. Again, let's start by making sure that our plots look good. So we need to affect our lines. Lines should be thick enough that everybody can see, even in the back row. Then font size, the same thing. Font has to be big enough. I don't know, let's try 20. Markers, sometimes we plot not lines, but some markers like dots or stars or something like that. They need to be big enough as well. Let's start with 20 and see if it's enough. All right, and then let's create a plot window, and let's clear it because we will run this file many times, and it's a good idea always to clear the figure so that not the previous stuff is there to confuse us. And then let's construct evaluation points, because whenever plotting functions in practice, we have to choose some points on the horizontal axis where we will plot the point on the vertical axis. So let's put x plot equals clean space. Right now I'm not completely sure what would be a good plotting area. We can change it later, but let's put here x minimum, let's say -1, and x maximum +1. We will change them if we cannot see what we want in this area. And then let's go from x min to x max, and since we are plotting linear functions, it would be enough to take actually 2 points, but it feels so wrong, so let's put at least 5 points, although it doesn't really make the plot look any different. Because Matlab uses, when it plots this finite number of points in the plane, it will put a linear connection between the dots. So if we plot like a parabola or something, we better have many points, because otherwise it will look like pieces of linear functions. But if we have enough, then we start to see the smooth shape of the actual function. But now we are plotting just linear functions, so that it doesn't make any difference if we have 2 points or 5. But anyway, then plot equation 1, and actually I don't have any equations in mind beforehand. Let's construct a set of 3 equations so that they don't have any solution. So equation 1, let's choose something like slope 2. Maybe that's good. Let's plot just this line going through the origin and having slope 2, and plot xplot y plot maybe red and line like this, and I always like to put here axis equal so that our plot has correct proportions. So if you would plot a circle, it would look like a circle and not an ellipse due to some kind of default aspect ratio. So let's run this and let's see what happens. Okay, so here we have a plot of our linear function, and we need two more. Let's make equation 2. For example, let's say -1 plus 2, something like that. And let's plot it in blue. And I think if we look at our plot again, I think the numbers are very small. I doubt that the back row can see them. So let's make these numbers in the grid points a bit bigger. So for example, let's so I use the command set and then GCA, which means get current axis. So this setting will affect the current plot, and I will put the tick marks on the horizontal axis to be, let's say, from x min to x max. This may be, well, sometimes x min and x max are not integers, so let's make this, for example, the closest integer, which is smaller than that one, and here smallest integer that's greater than x max, something like that. And now here, the whole point of this line is to put the font size bigger. So this is somehow the main point here. So if we run this one, something went wrong. Any idea why do we see only one function? Yep. Indeed, we should have here, hold on, that means that the next plot will be put to the same figure and keep this one. So let's run again. So now we see both equations. And maybe we could have some line here so we don't they will not overlap at all. Let's have a horizontal one. Maybe oh, this is equation 2, and then we need equation 3. It's enough to have those ones here. So, for example, third equation would be that y equals 1. And let's do that in what would be a good color? What colors are there? Green. Oh, that's otherwise a good idea, but you know, something like 1% of people have trouble with the green-red color vision. So for that reason, I never put anything plotted in a way that requires seeing the difference between green and red. So, well, let's put black and see how this looks like. Something went wrong. It should be once size xplot. It was just a scalar. Okay, so here we have it, but I think our view is a bit unfortunate. We should maybe see a little bit further to the right. So let's actually change our maybe xmin. Well, let's put here 3, for example. And so now our plot extends up to 3 here. So here we have now 3 linear equations, and clearly there is no solution to this system of equations. Actually, you know, the empty space here in the middle is rather small for this display. So let's change our black equation line to be actually y equals 0 instead of 1. Here, let's put zeros. Okay, and maybe it's also a bit unfortunate how there is so much useless space in this figure. I would like to actually see this figure from, let's say, y from -1 to +2, and x maybe from the minimum to maximum. So let's actually put here axis limits. So x would go from minimum to maximum, and y would go from 0. Did I say 0 or -1? -1 to 2, let's say. And maybe the other way around. Okay. This is more like it. This is what I wanted to see. So we now very clearly see 3 linear equations that have no common solution, and it's kind of shown very clearly in the area where everything interesting happens. Okay, so then let's solve this system of linear equations in the least squares sense. So this part of the routine is called plot. Plot the equations, and this we will just call parameters for plotting. Plot the equations, and then let's make a new place here. Solve the system of equations in the solve happens in the least squares sense. Okay, so first of all we need to build our matrix. So we have the matrix model is here. We have A times, then we have an X and Y. Let me write it this way. Equals B. where, so this is not MATLAB code, not really mathematical notation either. Well, I hope you get the point. So where A is a matrix of size, so what's the size? What do you think? How many rows in A? First row, what do you think? Matrix A, how many rows? How many columns? Okay, I'll give you a hint. For columns, see that the A matrix is multiplying a vertical vector with two elements. How many columns in matrix A? It's 2. Excellent. Matrix A has 2 columns. How many rows? Okay, the remaining students in the first row. Think, how many rows? 3. Yes, that's the number of equations we have. So, matrix of size 2 by, 3 rows, 2 columns. Here the number of rows equals the number of equations, and the number of columns is 2 because we have 2 variables. Thank you. Okay, so we have our matrix model, so we have to build our system matrix. So we need to see what happens. So each equation has 1 row. So let's look at our equation 1. So let me copy this one down here. Equation 1 is this one. So this means that, let's see, if we move this 2 times x to the left side of the equation, we see that there is minus 2 times x plus y equals, what does it equal? Second row in the class. What does it equal? 0. Excellent there. So we have here minus 2 and, minus 2 and 1 is the first row. The 0 will appear in the right-hand side vector B just in a minute. Oh, but now I need these. Okay. I can sense the fear spreading. The questions will come after you. Yes, yes. So we have equation number 2. Let's take it like this. Third row, you have still a minute to think about it. Equation 2 is this one. So, okay, what is multiplying x here? Third row. Is it? It's not. What should it be? It's 1. 1 times x. I'll remove it. And for y, one, and equals what? Okay, now the next row up there. There, what should? Excellent. And then we need equation 3. Equation 3 is this one. This is the equation, so well, it's actually pretty much already there. So I'll save you from that. Okay, so we have here 1 and 1, and in the last row we have 0 and 1, I think. Does it look okay to you? Excellent. Then we need a right-hand side vector. Right-hand side vector B. What's the size of this vector? Anyone volunteer? Vertical vector, how many elements? 2, that's one answer. 3 is another answer, which happens to be correct. And what are the numbers in this vector? There's a hint, it's called the right-hand side vector. So on the right-hand side in these 3 equations, we have those numbers. Okay, I'll just write them here. I know this is Finland, I know this is torture to you, but it feels so much better here, you know, to sometimes hear something from you as well. I'm talking so much up front here. Okay, it should be vertical. Let's do it that way. So now we are ready to solve our problem in the least square sense. Least square sense. So of course the matrix A is not invertible, so we cannot I mean, one could think of writing something like this. However, it makes no sense because A is not a square matrix. It just cannot have an inverse. However, it does have a pseudo-inverse. Why? Because every matrix has a pseudo-inverse. There is no problem in using the pseudo-inverse. So we get the result, and in the result will be a vector with how many elements? Now in the middle there, sorry about this, but I'm asking, how many components does the result vector have? Really? I mean, come on, you should know this. What are the unknowns in this problem? How many unknowns do we have in our problem? Yes, indeed. And that's why our answer must have 2 components, otherwise nothing makes sense at all. So x should be the first component of the result vector, and y should be the second component of the result vector. Okay, after all this torture, let's see if we can make any sense out of it. I'll run it. At least there was no error, and let's see. The result vector looks like that. Fortunately, it has 2 components, and I picked them out, so x and y are just the 2 components from the result vector. Now it's the moment of truth. We need to plot this least squares solution in the same plot than the equations, which will reveal if any of this makes any sense. And for that, I think I will move this plotting part of our routine to be after the solution part, because then we have available the solution. So now here plot least squares solution. So this time we plot only one point, x coordinate and y coordinate coming from the result vector. Yep. Sorry, please, can you repeat? Excellent question. What is the size of the pseudo-inverse? Let's take a look here. So if I compute the pseudo-inverse of A, it's this one. And actually, the size of the pseudo-inverse is 2 by 3. And why this is because what happens in the solution here is that our pseudo-inverse is multiplying the right-hand side vector. And the right-hand side vector has 3 components. So that's why the pseudo-inverse, it must have 3 columns. Otherwise, this multiplication makes no sense. And then, on the other hand, we know that the result must have 2 components because we have 2 variables in this system. So that's why the pseudo-inverse must actually have 2 rows. So the pseudo-inverse actually has the same size than the transpose of matrix A. Because the matrix A multiplies a 2 vector, and the result is the right-hand side vector with 3 components. But the pseudo-inverse has to go the other way around. It's applied to the right-hand side, and it will produce something in the result space which is 2-dimensional. So it has to have kind of the opposite. So if A has 3 rows and 2 columns, then the pseudo-inverse must have 2 rows and 3 columns. Good question. I hope this clarified. Okay, so now I'm getting really worried because we are about to see what is our solution. So let's plot it as, let's say, a black star and make the marker size as big as we described in the beginning. And I think I will move these axis setting thingies after the last thing we plot. I'm not sure if it makes any difference, but it feels better. Maybe I even call them axis settings. Okay, well, let's see what happens. I'll run this. Oh, not star. Let's see something better. Maybe we can just put a point. Okay. So our least square solution is there. I was kind of expecting it to be more in the middle, but that's where it is. At least it's inside the triangle, which is promising anyway. So of course the idea of this is the minimum norm solution, and its idea is to be the shortest of all least square solutions. Although maybe there is only a unique one here, but well, there it is. You know, I'm always surprised when I see them. I somehow have the mental idea that they should be more in the middle, but that's not always the case. Anyway, that's the least square solution, unless if we made some kind of a mistake, but probably not. Maybe not. I don't know if it's really probable or not. We can also try what happens if we use the Könökeppi operator. And we can compare like this. And let's plot I'm really wondering what happens. Let's plot it in red and a bit smaller. If we can make the marker size a bit bigger here. Ooh, let's see what happens. Well, as you can see, they do coincide. So I think that's where it really is, although I must say I'm always a little bit surprised where the solution actually is. But that's where it is. So it kind of finds, in some specific technical sense, it finds the point in the plane that simultaneously, in a best possible way, satisfies all of these three equations. Of course, it's just one technical sense in which to do it. We could, of course, define it also differently, but this least squares definition is a very useful one and a very standard one, a lot used in applied math. Well, I think that's what we have here. Let's have the break. Let's continue, let's say, in 10 minutes. Let's continue 11:50. My computer clock is 11:05. Let's have a 10-minute break and then go to the fitting to data points problem.